Welcome to the F+L podcast. Our guest today is Dr. Selim Erhan. Dr. Erhan is with Process Oils Inc., which is part of Ergon. He is currently Director of Technical Business Development. Welcome to F+L podcast, Dr. Erhan.
Thank you very much for your invitation. It's a pleasure to be here.
You're welcome. So, Dr. Erhan, tell us a little bit about yourself.
Hello, everyone. My name is Selim Erhan. I am the Director of Technical Business Development, working for Process Oils, which is an Argon company. And what we do, mostly process oils for the rubber industry, plastics industry, but we extend with our portfolio into several other areas: lubricants and greases, oil field drilling, and lubricant additives. We also look into asphalt. We look into dust control agents, agricultural sprays. These molecules are quite versatile, so we can use them in many different applications. And Argon is a naphthenic oil producer. It's the largest naphthenic oil producer in the world and in North America. But we also have paraffinic oils and vegetable oils. So mostly my expertise is in industrial applications of vegetable oils. I started at the United States Department of Agriculture, looking at various different applications in different industries. This was trying to help the farmers diversify their crops so they don't have to rely on one crop, and looking at helping besides food, where else it can be used. Because there is a lot of vegetable oil, and it doesn't really, like especially in soybean oil case, it doesn't endanger the food supplies. So we can use these. These are very valuable molecules, and they have high performance at a lower cost compared to some other high-performing esters. Of course, it's not for every use, but it can be used in various different applications. So I help our technical customers to see what these molecules can do. I help the sales department, the marketing department, and hopefully find new homes for these nice molecules.
So, Dr. Erhan, as you mentioned, Process Oils is an Ergon company. Now, Ergon is probably best known as being the largest naphthenic producer in the world. So, why would Ergon be interested in vegetable oils?
Because the company and the leadership, their main goal, it's a family company, and the main goal is to serve customers and satisfy customers' needs. So each molecule we should have has like a job security. The structure, the abilities serve a certain purpose, but not one molecule can serve everything. There is electrically charged areas, there are neutral areas. Some areas you need surface adhesion, some areas you need to stay away from the surface. So if you look at the structures, naphthenic oils are different than paraffinic oils, group 1 oils, group 2 oils, group 3 oil. They're all slightly different. Now, vegetable oils have a unique structure and can address very special needs. So if one looks at, let's say, these areas where naphthenic oils cannot service and paraffinic oils cannot surface, because Argon also has a paraffinic refinery in Pennsylvania. So they produce paraffinic oils too, mostly for the domestic market because of the location. But there are areas where, let's say, for instance, rubber. We're working in rubber, and vegetable oils actually work much better compared to a naphthenic oil, or especially like a group 1, group 2 oil. because of their polarity, because of their geometrical structure, because of their interactions with other additives. So there's a big difference in performance. But let's say if you take a vegetable oil and try to make an engine oil out of it, it will not work. So over there, naphthenic oils doesn't work that great either. You need a more neutral oil. So there is a lot of different applications with a lot of each one of them having specific needs. So if one has a portfolio where you can help the customer for whatever need they have, that is going to keep the customer happy, keep the business interaction going, and that is the goal of the company. So they are fully supportive of what Process Oils does, and Process Oils is operating independently of Argon.
So,
Yes.
so basically, Process Oils was an independent company, and it was purchased by Argon sometime in the mid 2000s. Is that right?
Correct. Yes, 6 years ago.
6 years ago, and actually, Process Oils does not manufacture any vegetable oil.
Correct.
And you purchase vegetable oil from a supplier, and then you start manufacturing, or what's the arrangement?
Well, we partner with one of the largest vegetable oil manufacturers in the world, or probably the largest, Archer Daniels Midland. They have a partnership with Wilmar in Asia. So this company has access to all the medium chain vegetable oils like soybean, sunflower, safflower, canola. They crush them and they produce them for mainly the food market, but also they have coconuts and palms coming from Asia through Wilmar. So this is a big portfolio because sometimes you need short chains, sometimes you need medium or long chains. And the company, another thing is when we interact with our customers, you need to have a steady supply. You need to be able to supply the market wherever you are because most companies are global. And we need to have consistency in the product. So teaming up with a large manufacturer guarantees all of these. If there's a shortage in Europe, we can get it from South America. If there's a shortage in Asia, we can get it from, let's say, North America. So there is a logistics advantage, quality advantage. So that is what we do for the vegetable oils. But there's also derivatives of vegetable oils that are necessary in some applications. Let's say like extra lubricity, extra performance. Then we specially toll manufacture these products that will be that needs more processing, that needs more reaction capabilities. So we have those made specially.
So explain to us which vegetable oils are short chain and which ones are medium chain, and how different are the applications for the short versus the medium?
Now, if you think of a lubricity application, lubricity is trying to separate two layers from each other so they can slide over each other. So as you can imagine, if you have, let's say, long spaghetti like molecules that would slide over each other and keep sliding and sliding and sliding and sliding, then you have a better protection of the surfaces. If you have short chains, they will separate quickly, showing bare metal surfaces, which may then have wear, adhesion, and friction. So in a application like a lubrication, where two surfaces needs to be separated as much as possible, you would need longer chains. So most, the ones we know as soybean, sunflower, safflower, canola, these all have 18 carbon chains, and they have a certain performance. If you need extra performance, there's high erucic acid rapeseed, mostly available in Europe. Those are 22 carbon chains. So if you compare them side by side, you would see a difference. Now, there is also another world where you need to make emulsifiers, which could be personal care with face creams, hand soaps, surfactants, dish soaps, laundry soaps, where you need these molecules to bunch up together and they will form a sphere, which we call micelles, that can house oily material. So if you want to wash your clothes, um, the surfactant lifts off the oily material and the oily material goes into the sphere, and the sphere is then held in water and washed away. So you can imagine if you want to make a sphere, well, then you really need shorter chains. They can bunch up easier, they can fit into that structure, and you will form much manageable, much more easily controllable micelles or these balls. So in the surfactant world, surfactants, personal care materials, detergents, those mostly use shorter chain fatty acids, which is coconut and palm. We're talking about 10 carbons long, 8, 10, 12 carbons long. There may be 14 and 16, but it doesn't go to 18. So those are more beneficial. Let's say another application where you need corrosion protection. So you need to cover the surface of a metal to cut off the air. And there you would need something like a carpet. So you have short chains that just line up and stack together very nicely and form a surface like a carpet, which excludes the air and keeps it away from the metal surface. There again, you need short chains, actually shorter chains. They say 8 carbons long, 10 carbons long. That's where you would really need the short chain like coconuts and those kind of short chain vegetable oils.
Can we make a generalization that the shorter chain vegetable oils go more into personal care applications and therefore are higher value, whereas the medium and the longer chains vegetable oils go towards more industrial applications and have, I would say, lesser value in the marketplace? Would that be a correct statement?
Yes, correct. Correct, because the higher the demand, the price then changes accordingly. It's not because of the more purity or the processing cost, but it is the demand. So the cosmetic industry, a personal care industry can afford to pay more because they use smaller amounts, and also those things last longer. You don't like buy and every day use tons of, let's say, facial cream. So if a facial cream lasts for several months, well, then they are not going to be able to sell much of it. So they need to compensate for that cost. And there's of course a very, very complicated cost balance. But in general, what you say is very correct.
Now, you've spent a long time in the vegetable oil industry. Um, what are the biggest changes you've seen over the last 20 plus years you've been involved?
Well, there is a lot of change in the industry continuously because there's constantly new innovations coming up, new needs coming up. For instance, there has been quite a bit of change in the metalworking industry, in the lubricant industry. The metal, for instance, one leads to another. We need to be more careful about fuel consumption because it's related to the climate and greenhouse gases, so and global warming. So when you want to cut down on, let's say, this fuel consumption and rely less on fossil fuels, then it opens up a whole host of demands and needs. First of all, you need, let's say, lighter vehicles that would need less fuel or keep going longer. So when you mean lighter vehicles, then you start looking at the metal, you start looking at the weight of the car, and instead of going with thicker steel, you want to go with high strength, thinner steel. Same strength, but it is thinner, it weighs less. You need maybe more plastic parts, you need more lubrication in your engine. So when you go to these very high strength metals, they are very difficult to machine. That opens up a need for much better lubricants, much better or different surface interactions. When you look at engine oils, you want to reduce the internal friction, again, to spend less fuel on unnecessary friction. So when you want to reduce the internal friction of the oil, then you need to use lower viscosity oils, less and less viscous, which means you don't have much lubricity left, which then opens up the door to having to put in better performing lubricants. Then that affects the paint industry, that affects the plastics industry. You need, let's say, better plastics in, let's say, cars. Again, I'm just taking one example, just this automotive industry. Then you need to have, let's say, UV protection. You need to have better adhesion compatibility, seal compatibility. So everything is linked to each other. So one change or one need in one area cascades down to all the other industries. Then there's a heightened need for, let's say, health and safety, because we start realizing in the turn of the century that a lot of the chemicals that looked good or performed well were actually not as good for our health, and started getting associated with a lot of very serious diseases. So you need to start looking at, well, what else I can use? Let's say in tires, aromatic oils were excellent, and it was under everybody's impression that you put the oil in, you vulcanize the tire, everything sets, and you have a nice product, everything is sealed. Well, but the oil doesn't get attached to the rubber matrix very well. So throughout the life of the tire, it starts getting squeezed out, which ends up on the road and the water systems, the creeks, oceans. So they said, okay, these aromatic oils we know have some negative effects on health, so we can't use it. So the industry starts looking for a replacement. And usually the replacements are not that easy because it takes a long time to develop these. So that need suddenly opened up a whole world of looking at process oils, what other process oils there are, what is important, who does what inside the formulation. And so that change came up. And then recently, sustainability and life cycle analysis, where the product is coming, where it is going, not only the area we are looking at it, but all the way back, all the way forward. This way we can guarantee a safer and more sustainable world for our children, for the next generations, and ourselves, and address things like global warming, which are getting more and more severe. So it is complicated. Everything is interconnected. A change and a need in one area opens up another one. So I would say sustainability, health concerns, and a desire to move towards less dangerous materials is the main driving force behind most of the new developments.
Now, Dr. Erhan, performance in the past has always been an issue with vegetable oils. Has that been resolved, and with what and how?
Now, like I said, the performance is related to the area. Let's say if you try to make an engine oil from a vegetable oil, the vegetable oils have a lot of double bonds. These double bonds are there for a reason. It keeps the molecule flexible, it keeps it liquid, it keeps it from freezing for the plants, because that's why the plants make it. And it serves that purpose. So if you want to use it in a, let's say, increase your solvency, it's a perfect molecule. It will do a great job. If you want to increase your polarity in your mixture and carry materials that would be otherwise difficult to carry, like, let's say, again, we're talking about, let's say, rubber. You have antioxidants, you can have anti-ozonants, sulfur packages, a lot of metal oxides, you have carbon black, you have silica. You need to move these inside a relatively non-polar matrix. So those double bonds, those chain lengths, those geometrical structures are perfect for this purpose. But if you try to take the same molecule and you try to put it in an engine oil, those double bonds start opening up very quickly, and you start breaking chains, you start losing chain length, you start losing lubricity. Those small particles start coming off, and they start smelling bad. They form acids, they generate corrosion. So an application where the vegetable oil is absolutely great in a rubber tire would be absolutely horrible in an engine oil. So now we know what these problems are, right? And so if you can put more antioxidant in it, then you can prevent the oxidation. If you use a more closed system, then you can prevent oxidation. If you are using a metalworking fluid and you think that these will grow bacteria more, then you can put more antibacterial agents. So there is a cure for every one of these issues, depending on where they are being used. The question then becomes the finances, because if you use oil A, you are going to use less antioxidant, which is expensive. Oil B, you need to use more antioxidants, and then you never know if it will be okay or not 3 years down the road. So when you start evaluating these, because the ultimate desire is to have a well-functioning product, you don't want to change your engine oil every 2,000 miles or 1,000 miles. You don't want to, let's say, have issues with your, let's say, paints, and so on. So it works back from the actual need, and in some times it is the cost also that plays an effect. But usually, in my experience, it's always the performance comes first. You need to meet that performance, and then comes the other aspects, the logistics, the price, and so on. So yes, we know the cures for these problems. We have solutions for it, but depends on the cost. In some areas, it's not worth going through that extra cost. In some areas, there is no problems. Actually, it works better. So, I mean, just like, for instance, the Statue of Liberty is running on hydraulic fluids made out of soybean oil for the last, 20 years. No issues, no problems. Yes, depends on the area, depends on the solution. Sometimes it's great, sometimes it's a little bit too expensive, so they put it on the back burner.
So, Dr. Erhan, let's talk about the exciting, promising growth markets for vegetable oils. You mentioned rubber. That appears to be one of the most promising areas, isn't it?
Yes, because vegetable oils in this case bring a lot of advantages. It brings, let's say, low temperature properties. The glass transition temperature is very low. It's around minus 90 degrees centigrade, which makes it an excellent choice to use in winter tires, where you need the rubber to stay soft at very, very low temperatures so it can adhere to the road. But also in regular tires, they work great. So slowly and slowly, the industry is looking at expanding the market using vegetable oils. Of course, depending on the industry, it might be a very, very delicate use area, which rubber is, tires are, because our life depends on it. We are riding on it, our children, our families. So you want that tire not to fall apart. Therefore, the companies are very, very careful when they change raw materials. They need to study this in every possible way before they will accept it as a new replacement for whatever they were using before. Some areas are easier to go into. Let's say drilling fluids. That is also a growing market because the new areas that people are drilling in could be offshore, it could be close to aquifers. So if you use a more, let's say, toxic lubricant, gets into the water supplies, then there are very serious issues, health issues, disposal costs, and so on. So an area like that where water and aquifers are concerned is a growing market. Marine lubricants, where the oil goes into the sea, that is another growing market. But also there are some very unique areas where these things have shown remarkable performance. Let's say inks, newspaper inks. Now, not many people are reading newspapers anymore, so it's a dwindling market. But there, soybean oil, for instance, performed extremely well. You know, you don't want the ink to go to the other side of the paper. You want it to penetrate right into the middle and stay there. And soybean oil did it perfectly. So that was a big area, big discovery. You also can use this in asphalt. So asphalt is a big industry. So a lot of roads are covered with asphalt. And it turns out that, let's say, vegetable oils, specifically soybean, being more abundant and much cheaper, it does really a remarkable job in rejuvenating old asphalt, which makes old asphalt usable, which then cuts down on fossil materials, fossil fuels, and fossil oils, because you can use the ones that already is out there. So that's another big area that we think vegetable oils will find a lot of acceptance. Lubricants, specialty lubricants, those are growing because we are using more and more, let's say, difficult alloys, difficult materials to machine with. That's another area that is growing. Corrosion inhibition, pipeline corrosion inhibition. These are all areas that we expect growth in these molecules.
So you're saying that the market is growing, not shrinking, for vegetable oil. Are they replacing fossil-based or conventional products, basically? Is that what's happening?
Well, depends on the use area. Some areas you can, some areas actually you cannot. For instance, if you want to use a gear oil in a gear that is going to last for a long time, let's say we're talking about wind turbines. Those are very expensive, and once the gear is in there, you expect it to last for maybe 20 years. Well, that oil has to be there. It is changed, of course, but it has to be stable under very severe conditions: heat, lightning, water, dust, oxygen. I mean, there's all kinds of contaminants constantly in the environment of that gear oil. So there, if you try to use a vegetable oil itself, it's not going to work. It will, like in a couple of months, that gear will lose its oil and have very serious issues. So there you need to use a very, very neutral oil that will last for a long time and will not be affected by these very harsh conditions. So in that case, I mean, actually, in those, well, you can't use it everywhere. It cannot replace every type of molecule. It has a specific structure, therefore a specific functionality. So if the application area meets those needs, the things that they can do, it's great. Otherwise, it is not. As let's say, You have a Ferrari, it's a great car, it goes fast and everything, but if you want to go to Menards and carry a couple of cement bags and some lumber, it can't do that, right? So it's not designed for that. So then you need a, let's say, pickup truck to carry those things, and you are perfectly happy with it. So there is a structure, a molecular structure for every purpose that is out there, and it's not as simple as like changing and pouring one instead of the other one. Some cases it works, some cases it doesn't. But these areas that we just mentioned are growing, and they are perfectly suitable for vegetable oils. So we see some increase in these markets.
In your work, do you see additives that are used for the regular products, the conventional products? Do they also work with vegetable oils, or do you need a different additive to work with vegetable oils?
Most of the time, different, because the structure is different. Something that is made, let's say, again, if we picture spaghetti chains, there's something that will, let's say, be suitable to use with that kind of a structure is going to be quite different than, let's say, a highly branched, more polar material, which is the vegetable oils. So usually the dispersants, the viscosity, the things that will increase your viscosity or decrease your viscosity, 4-point depressants, dispersants, these molecules, these additives will be different for vegetable oils compared to, let's say, mineral oils. And that is also one of the issues that, let's say, formulators have. You have a formula with maybe 10 components in it. You want to change the oil and put in this vegetable oil in there, and you don't change the other ones, or you don't evaluate it. That would lead to problems. So yes, the formulas have to be completely revised. Let's say we're talking about rubber. If you just replace the mineral oil with vegetable oil 1-to-1, it doesn't really work because it uses up the sulfur package. You have less sulfur now to build up your cross-link density. Your tire is softer, and then you start having issues. So if you are going to use a vegetable oil in a tire, then you have to look at the other components too and make sure that you have a balanced formula according to this new structure that you are using.
The additive suppliers for vegetable oils in, for example, let's just say one industry, metalworking fluids, are they specialty additive suppliers, or are they one of the big four, for example, that focuses on addressing the needs for biodegradable vegetable oil type products?
Additive suppliers are actually, yes, it's a complicated industry. When you say, let's say you are making a metalworking fluid formulation and you need maybe 10% of a lubricity additive. Well, you look at the lubricity additive, and if you look at those additive packages for lubricity, it's not 1 or 2 components. It's usually 3, 4, sometimes 5 different lubricants in there. You look at an emulsifier, let's say, for drilling fluids. And when you look at that emulsifier company, that is like the additive company that's for giving you the emulsifiers, those emulsifiers are usually 3, 4, 5 different components. And there's an emulsifier for high temperature, there's an emulsifier for high pressure, right? Or a lubricant for, let's say, heavy duty, lubricant for light duty. So in each specific area where an additive needs to function, there's also a lot of different needs. So an additive company spends a lot of time specifically on addressing each one of these: light metal, heavy metal, high pressure, low pressure, and they have a series of additives that is each composed of 3, 4, 5 components that will address these. So the formulator, all they have to say is, well, I need to use, let's say, it's a very high pressure action, and I have some steel, but I also have some copper in there. I need a suitable additive. Then the additive company says, okay, this is the package that would work best for you. And usually it is like this for almost every area, like defoamers. Those are not one components usually. Corrosion inhibitors. Those are also complicated structures. You don't have like one, but maybe 3, 4, 5 different components in a corrosion inhibitor package that would be provided to an end formulator. Because let's say, are you coating the bottom of a truck? Are you covering up a metal part? Are you using it in a pipeline? Is the pipeline carrying asphalt, or is it carrying let's say, crude oil that will have water and gas mixture in it? See, all of these needs would require different corrosion inhibitors. So the additive supplier is going to look at all of these and find solutions for each one of these and have these packages ready. And when the user needs it, I need it to use it on my truck, well, they say, okay, you need this package. So it is additive suppliers also follow the changes, the different needs, and they start preparing for it way in advance so that when the need hits the market, they have a solution for it.
Are there industry specifications for
Of
vegetable
course.
oil? ASTM test methods? Tell us a little bit how that works for
yes.
specifically for vegetable oil.
Well, depending on what you need to measure. Let's say, in the case of vegetable oils, nature makes them. And nature is very consistent. So you get, let's say, soybean oil. It consistently provides you with a structure year in, year out. So there's not much you can do or need to do about it. But let's say if one needs, where does it freeze? What is the pour point? And if I say -6 and the other one says -10, well, I mean, which one is correct? So that then depends on the test method. So most of the specifications are, all of them actually, are around the test methods. So there is testing bodies like ASTM. They look at flash point, pour point, freezing point, those kind of measurements. Viscosity, because the viscosity changes with temperature and it's a very sensitive measurement. So how do you measure the viscosity? So these things are standardized with a group of chemists that come together, they carefully evaluate, and they write down a procedure that could be followed wherever you are in the world. American Oil Chemists Society, AOCS, has most of the standards for these tests for vegetable oils. So those two, and of course in Europe, there are different test methods. So there is several test methods for, let's say, biodegradation, freezing point, flash point, those kind of numbers that people need to decide how they can use it in their applications. But there are standards, and these are studied since 1920s, so they're well established and suitable for all the modern equipment that we have today.
Why is the OECD involved in, I believe it's the biodeterioration, isn't it?
Yes. There are different different environments. For instance, is your material going to end in landfill? Because there's a different set of bacteria in there, less water, no oxygen, let's say, and is it going to degrade over there? And those conditions are, of course, completely different than if the material ends up in a lake, where there is, let's say, it's not salty. but there is some sediment. Or is it going to end up in the sea where the water is salty? And is it going to stay up? Is it going to go down? What kind of bacteria it will see? So depending on where this material is going to end up, they devise a test method that could duplicate those conditions. So there's OECD, let's say 301, A, B, C, D, E. So that determines what kind of a test method and what kind of bacteria you need to use that could duplicate that environment that you are targeting. So it gets more. There's a lot of variety in these tests because of those needs.
But those tests are actually very short tests, like 28 days or something like that. Or is that sufficient to test a fluid's biodegradability?
Well, let's say vegetable oil would degrade in less than 10 days. So, for instance, one requirement, if you wanted to have a name, let's say readily biodegradable, yes, they look at the 28-day test, but if 60% of it degrades in less than 10 days, they say, okay, well, this is very quickly deteriorating. And that gives some kind of information to the user. If you have to wait 3, 4, 5 years to see if it degrades or not, then it is passing the lifetime of many researchers. So
Yes.
you need to have a more reasonable time. So that's where a lot of these test methods takes time to develop, because they say, okay, what is the reasonable time? What is a time that can give us an idea about the future? What is, let's say, if you want to take a tire and do an aging study on it, like you can't wait 4 or 5 years to see what happens to the tire. You need to know it quickly. So, okay, you put it in an oven, you increase the temperature, you need airflow, you need some pressure. And then a group of people sit down and go over these needs and try to come up with a reasonable time that will give the best information possible. And then, of course, they're always revised, depending on new information, depending on new equipment or instruments that come up. So they are constantly revised, constantly scrutinized. But that is the reason why sometimes you have 28 days, sometimes 30 days for a biodegradation test, or 3 days for, let's say, an aging study. So
Yeah. Well, to me, it just sounds like 28 is a very odd number for a test. That's just my personal opinion. Why not 30 days, which is 1 month, or 15 days, which is shorter than 28? So anyway, I'm sure there's a story behind it, but
of course, there's a technical need, and sometimes they need to have a break and go on vacation or something.
yes.
So it's not 30 days, but 20. No, these things are studied very, very carefully by many scientists on this panel, and it's very carefully designed. So it is not just a number that is picked up. It is years of study that come up with these time frames.
So, Dr. Erhan, I think it's been a very interesting discussion. You've touched on a number of growth areas that are the most promising for vegetable oils. Regionally, which area do you think has the most promise? I believe process oils is primarily doing business in the United States, although I also heard that you are going overseas now. But as far as you know, what region has the most promise for this particular product?
Well, the Asian market is the fastest growing market. There is the population increase is much more compared to Europe or the United States. and therefore the needs for items is much higher in the Asian market. So the growth, the manufacturing capabilities are much different, much higher. The Asian market is newer than the European or US market. So they have the advantage, I believe, of newer equipment, more sophisticated equipment, which may require a different type of, let's say, additive. So the growing market, the biggest market is in Asia, as far as quantity and types are concerned. Europe is a more saturated market, a more mature market. And of course, United States, there's new areas that are opening up. United States, Canada, but United States having the highest population. And Mexico is a growing market, highly industrialized, and serves Latin America. Brazil is a large country, 300 some million, a big industrialization effort. So that's a growing market. And besides that, companies are quite global because they try to strategically use raw materials with manufacturing and with the needs of the people. So there's a very delicate balance. So these companies, let's say you're taking a tire company, they have manufacturing sites in North America, South America, Europe, Asia, and Asian tire companies have manufacturing sites in Europe, in North America, South America. So they need the same quality of raw materials wherever they are. So something that is supplied to them in Asia has to be the same in Europe, has to be the same in US, has to be the same in South America. And when the market has become global, that pushes the companies that are providing to go global too. So you have to look at the logistics, you have to look at the cost issues, performance, manufacturing, and those and availability. So those things has become global and interconnected. So yeah, it's a growing market, but the industry and the supply is growing together with it, and it's truly, really global.
Now, in the EU, there is a tire legislation. In Germany and Austria, and I believe a few other countries in Europe, there are labeling for biodegradable oils. Do you know of any legislation or anything similar in Asia that's going on that promotes the use of vegetable oils in industrial products?
Yes, of course. I know China has mandates to lower greenhouse gases. Korea has, Japan has, Indonesia, Malaysia, Thailand. They have legislations trying to promote safer products. Together, we're trying to save the environment, preventing the jungles from being lost with the habitats inside it. So there's a lot of international legislations that percolate from one area to the other. Because let's say a tire manufacturer has a specific specification in Europe. Well, are they going to have different requirements in different areas? They say no. We just need the same. Because you can take the tires from Europe and sell it in the US or sell it in China. China can have tires that they may be selling in Brazil. So because of this ease of moving things around with the container ships and so on, the manufacturers are forced to abide by these legislations. If something comes up somewhere, the other ones start adopting it as quick as possible. And then this way it forces the additive manufacturers to abide by those legislations. So sometimes one area is leading and the other ones are following, but eventually and quickly they get harmonized.
So it's a global world, basically. And the industry benefits from it because you can manufacture standard products anywhere in the world and sell it anywhere in the world.
Correct, correct. And that's a good thing for everybody.
I believe
Because
so.
the behind the scenes, you have health concerns which are addressed. You have global issues like global warming addressed. You have, let's say, saving the forest, saving the jungles, saving the trees. Those are addressed. So behind these, there's all these protection mechanisms for us, for our children, for the environment. And this kind of globalization helps everyone, because the pollution one place also globally travels to the other side. So you can't isolate yourself. So everybody is working carefully together and getting more and more integrated, as the markets gets more homogenized.
I think so. Well, Dr. Erhan, thank you so much for your time, for sharing with us your knowledge. And it's been a real pleasure to have you on F+L Podcast.
It's my pleasure. Thank you for the invitation.
You're welcome. Have a good day.
You too. Bye-bye.
Bye-bye.